All right, here we go. So, we've been eating our chocolate covered grapes. Why do you have chocolate?
Exactly.
Hey,
we're trying to figure this out.
Okay, I digress. Here we go. We're not messing around today, people. So we got reflecting graphs. So this is going to lead us into inverse functions. Do you guys remember that stuff from Algebra 2? What do we remember about inverse functions? We switch x and y's, right? We solve for y's. Graphically, what was the trick to doing graphs of inverse functions? You could do it based on the new equation, but also you could do it based on the old graph. What was the trick when you wanted to graph the inverse function?
If it's like up here, then it sounds right here.
Yeah, okay, so we're flipping over something. What was the thing we were... Okay, there we go. We switched our x's and y's. There you go. Good job. All right, so this is leading into that. This is going to just talk about the reflected graph piece of it. Now, I can take any equation, and I can create a graph from it, and I can take that graph and reflect it over anything. And that may or may not be a new function when I regenerate this graph. It may have an inverse, it may not. So we're going to take a look at just reflecting today, and there's a couple places, or a couple things that we need to be alert to here when we're talking about reflections. You can reflect over lines, you can reflect over a point, and we're going to talk about some of those cases today. So this is a lot of FYI right here, right? A lot of writing stuff down. If you don't catch it, go back and check out YouTube or Blackboard and then get the rest of the information. But in quick mode here, a line of reflection. This is the line that is in between 2 points of a curve. These 2 points would be corresponding locations. So if we think of a parabola, you've got a point on the right side of the axis of symmetry. You have a point in the same y value but different opposite x's. And that's an example where you have a line of reflection, or in that case, an axis of symmetry is the same thing as a line of reflection for a parabola. In this case, we are going to be talking about, for inverse functions, a specific line of reflection of y equals x. It's like a mirror. So whatever happens on one side of that line would be reflected on the other side. Like Chloe was saying, we're going to take one side and flip it over to the other. You could also have reflections of x-axis, and that means you're going to flip your y's. You're going to change your y values, positive, negative, opposites. You could have reflections of the x-axis, or the y-axis, excuse me. And this is the one that we don't usually spend a whole lot of time on. In fact, I don't know if in Algebra 2 you guys did any horizontal reflections, but they do exist. And this is when you would switch right and lefts. So you are switching your, in this case, x values. They're going to be opposites of each other. So it's really just paying attention to that, right? Reflection over the y-axis, your y values become opposites of each other. Reflection, or excuse me, x-axis. Reflection over the y-axis, x become opposites of each other. In terms of the function notation from the original y equal f of x, our x-axis reflections we know as our vertical reflections, and they have the negative that sits out in front of the function itself. Negative quantity x plus 2 squared minus 3 tells me my graph is going upside down from what it normally would. The new function where I have horizontal changes, notice that the negative is now on the inside of the function. So if I had, for example, back to a quadratic, in the parentheses I had a negative of an x plus a 3, for example, squared, and then plus or minus another number. That negative on the inside tells me that I'm going to flip the graph right to left instead of flipping it up and down. So that's new for us, is this inside negative, what it does. Some graphs, like a quadratic, when you flip a right or left, it doesn't change the way the graph looks. It looks the same because it's symmetrical around the y-axis. And then, let's see, the reflection of y equal x, we talked about that, and that's where we're going to take our y and x values, and we flip them. What was an x becomes a y, and the same thing, y becomes an x. our symmetry case for our inverse functions. And then the last one here, what about just going and being reflected over some point? It may be the origin, and if that's the case, then you switch well, you don't switch. You change the signs of your x's and y's. They become opposites, both of them. And if that happens, you have reflection around the origin. So that's kind of where we're headed. You good there? So what we want to be able to do today is, one, can we graph these reflections from their original functions? And then, is there a way to be able to tell if a function is going to have a reflection and what type of reflection will it be, just by looking at the equation? And there is a way for us to do that. We don't have to graph it. We can do some manipulation of the original equation and see if we get back to the original after we make that manipulation happen. I'm going to scroll down. Are we still right? I can scroll down. Good. Oh, about it. I think this is it. Can I go up here, or did I lose somebody? Is that all right if I go there? Is that perfect, right? All right. Symmetry, we know this concept of symmetry. Like a book, for example, the right side of the book and the left side of the book are symmetrical. They reflect over the spine of the book, which is an axis. And again, points of symmetry, like what shapes? And if well, maybe we have no. But what shape do you think would be symmetrical around a point? Circles. Circles, yeah, circles. Other ones? What about other ones? They're in the same family. Conical family. So sphere is a volume thing. That's true. It is symmetrical around a conical point. We're talking about, huh? A sphere, an ellipse. Yes. Yes. An ellipse would also be symmetrical around a point. All right. So should we take a look at some of these things? So exciting. Second period, we were talking about roller coaster rides. I don't think we're going to talk about roller coaster rides. Can't get the roller coaster. I don't know. I just can't get the. There's no relate. Well, there wasn't even a relationship to the roller coaster ride with the last thing. But we were talking about it for some reason. Oh, it's because of the excitement level. You know, you get in the roller coaster, right? Your heart starts to pump. Whoa, going on a ride. And then you start to go up the track. Now your heart's pumping even faster, and so on. So we were just using. What? Am I telling stories again?
No.
Babbling on. All right, so here's that part where I said you could tell based off of just the equations. You don't have to graph it whether or not you have symmetry. So we're going to test these for all four of those cases and see if we have symmetry on any of them. And then we will look at the graph so we can get an idea. Remember, what's our default way of finding the graph of any function? What did we say we use? Huh? What can I do? I can plot points, right? I can create a t-table, pick some x's and find some y's. Hopefully there's going to be some functions that you recognize the parent function for, and then you be able to use those, come up with the graph a little quicker. But you can always go back to the default. Like C and D here in this example, those we don't have parent functions for those. We've never looked at those before. So we're going to put a t-table together for that. All right, here we go. Y equal x cubed. Who remembers what it looks like, first of all? Do you remember what it looks like? Okay, it's a kind of a vertical S-looking thing. So thinking about the way it looks, do you think it's symmetrical around the x-axis? Is there symmetry there? I got some heads shaking? No. How about y-axis? Is there symmetry around the y-axis?
Yeah.
Oh, we got some yeses. How about the origin? Are we symmetrical around a point?
Yeah.
And then how about around y equal x? Would we be symmetrical around that? Okay, maybe not so obvious on that one. So we got to vote for no on the x-axis, a yes, I heard, for the y-axis.
Yeah, we voted yes on the x-axis.
Oh, you voted yes on the x-axis. My, that shirt is bright.
I know.
That's
Because
awesome.
you all turned around
All right.
at the same time.
Okay, can I borrow that when I go around the corner? I actually have one. It's yellow. It's better than that. All right, and then we have origin and y equal x. All right, so here we go. We're going to test. If I want to test x-axis symmetry, I make the y's opposite. So I rewrite the equation with a negative y. And then I solve for y again, seeing if I get back to the original equation. So if I have to divide by negative 1 here, I get y equals negative x cubed. And that does not equal y equal x cubed. So therefore, there is no symmetry around the x-axis. No symmetry there.
What would you do for the y-axis?
Great question. So if I switch the y's for the x-axis, what do you think I switched for the y-axis? I switched the x-axis. So we're going back to this, right? Reflection in the x-axis, the y's are opposites. Reflection in the y-axis, the x's are opposites. So I'm just using this and applying that in these rules right here. You cool on that? All right. So now we go with y-axis. We make x is negative, negative. Now put in parentheses because we are there. That's what we're doing. And y equals negative x cubed. Again, not the same thing as y equals x cubed. So no, we do not have symmetry around the y-axis. Origin, we make them both negative now. Negative y equals negative x cubed. Divided by negative 1, divided by negative 1, and look at that. We now have symmetry. Get back to the original equation. Symmetrical around the point. Yes?
Why do you do negative 1?
Why am I dividing by negative 1?
Yeah.
I'm just dividing the negative out of there. Can't be a 2 because there's no 2 in front of y, right? So there's a 1 in front of y. It's actually a negative 1 in front of y. All right, so there's our only symmetry so far. And then y equals x, we flip. Make the x become the y, make the y become the x. So now this is x equal y cubed. Solve that for y, and we will get y equal to the cube root of x. And that is not the same thing as y equal to the x cubed. And so because they are different, there is no symmetry there as well. Okay, now let's go look at the graph and see why is it only symmetrical around the origin. Okay, here we go. Oh, pink. There we go. There's our beautiful graph. Now, for those of you who thought there might have been symmetry around the x-axis, if there was, just pick a point for example. Let's say we're using that point right there. If there was symmetry around the y or the x-axis, then there would have been a point at what? Negative 8. To negative 8 there would have been a point. So there is no symmetry. I don't have a reflection of that red dot on the bottom side of this graph. So there's no symmetry that way. If we think about y-axis symmetry, once again, the red dot, there is no reflected image of it on the left-hand side. So no symmetry. Yes?
It's the same with the cube functions.
Well, for this generic one, yes. Some cubed functions won't be symmetric around anything. Like ones that are like, for example, y equals x times x minus 1, x plus 4, there's no symmetry. There's no common point that is symmetric. Parent function, yes. All right, so there's why it's not symmetrical around the x and the y. Why is it symmetrical around the origin? Well, here's why. If I took those 2 points that are corresponding, 2, positive 8, negative 2, negative 8, and I looked at a line that connected them, and I took a look at the midpoint of that line, well, the midpoint of that line would cross at the origin. And if I kept doing that, if I picked points all along that curve, corresponding points, positive 1, 1, negative 1, 1, and I connected them with a line and found that line's midpoint, they would all be at the origin. So there's why you have point symmetry versus line symmetry. Isn't that amazing? All right, let's take a look at I think it's okay, well whatever. value graph. We know what it looks like. I hope you know what it looks like. So we conduct our test. We first of all make y's negative. Divide by -1. And y equaling the negative of absolute value of x is not the same as y equal the positive absolute value of x. And so we do not have symmetry around the x-axis. So we keep doing it. We keep testing all these things out. So now we're going to switch our backs.
Negative would be on the outside of it.
Pardon me?
Why is the negative not inside of the...
Great question. Because I'm dividing by -1. I'm taking an absolute value and dividing it by -1. So it's got to stay on the outside. Now we put the negative on the inside. Oh. But that's the same thing as saying just that. Right? And so here we do have symmetry. We have symmetry around the y-axis. And we know that. It's a V. So there is some symmetry. You got a line, vertical line there, split right in two. All right. What about a point? Switching both of them, -y equals absolute value of -x divided by -1. I get y equal negative value, absolute value of x. So once again, no symmetry there. And then lastly, switch them. X equal absolute value of y. Those are not the same thing. And therefore, once again, no symmetry. Right? So no, yes, no, no. Oh, yeah. Do we need to see what this looks like? Y equal absolute value of x? Anyone need to see that graph? Okay. So what does that one look like? It is a V. And it has the movements of -1, 1, 1, 1, and then -2, 2, 1. Okay. There's your symmetry. Why is there symmetry there? Because if I pick 2 points, corresponding points, right? Those two. And I look at their perpendicular bisector would be this axis. So you have symmetry there. Once again, capital A for amazing. Never stops getting amazing. Never. Just keeps going more and more amazing. All right. This one, these two, why don't you try those on your own here? See if we can come up with the symmetry tests, and then we will look at what a graph has. Where is it?
Can you read off the questions?
Say that again. Let's see what happens. I bet what happened when you guys were doing your testing here, like x to the 4 plus negative y to the 4, when you take an even power of a negative number, what do you get? It becomes positive. So if x to the 4th plus y to the 4th equals 1, yes, there is symmetry there.
Wait, so it was out of the parentheses?
Yes, it would be out of it, right. Out of the parentheses, it would be no. But what I'm doing is I'm making y negative, and it's negative y to the 4th.
When is it out of the parentheses? When you divide that?
When I divide by -1. So that means on this next one, when I make x negative and I raise it to the 4th power, I'm going to get the same thing. X to the 4th, y to the 4th equals 1. So that's a yes also. And then if it works on those two, then we know when we switch both of them, it's going to work. So this is going to be a yes. And then if we switch y's and x's and make it y to the 4th plus x to the 4th equal 1, that's the same thing as x to the 4th plus y to the 4th equal 1 because of the commutative property of addition. That means that's going to be symmetrical. So this is symmetrical around everything. So what does it look like? Well, funny you should ask.
Wait, what's the origin one?
What's the origin one? Yes.
Negative x to the 4th minus y to the 4th.
Negative x to the 4th becomes x to the 4th. Negative y to the 4th becomes y to the 4th. So here we go. There's what it looks like. Look at that little doodad. Where is it? Wait for it. There it is. There it is. Kind of a. Oh, I heard something. Did you really say it was cute? Somebody said it was cute. Did you say it was cute? Did you say it was cute? She said it was cute.
I thought it was a cube.
Oh. They said, oh, yeah, cute.
It's like cute.
Yeah, kind of a square with rounded edges, right?
Yeah.
Yeah. No, you said it was cube.
No.
You really did.
I didn't say it. I heard cute.
I heard cube too. Thank you, mullet man. All right. So that's what it looks like. Hey. Go away. There we go. All right. How about this one? Who got a yes on symmetric around the y-axis? Okay. Anyone have a yes on symmetry around the? What's this? Okay. X-axis, y-axis. Any y-axis symmetry? Any point symmetry? Okay. And then any y-axis symmetry? All right. Let's see here. What color should we use? Color of the day?
Green.
Purple. Green won't show up. So we make our x's negative. And I'm trying to. Oh, I'm doing the wrong one. Sorry.
Jump the gun there, dude. Jump the gun.
How to get it right?
Go ahead. Go ahead and tell me.
X times
Okay. This is what we end up with. So no symmetry there. Then we do the same thing over here. Now I make negative x, y cubed equal 1. Again, no symmetry. Switch both of them. Negative x times negative y cubed equals 1. So this becomes xy cubed equaling 1. So yes, symmetry on the point. And then switch them. Y x cubed equaling 1, solve for y. 1 over x cubed is not the same thing as y cubed x equaling 1. So, no.
Wait, doesn't the cube apply to the x or no?
The cube applies to the x, that is true.
No, in the
In what one now? That's like in the original problem? No, because there's no parenthesis around x and y. It's only applying to the base y. Yes?
Why did you get y by itself on?
Well, I didn't have to do that. Just so you can see that it's a reciprocal function, so you're going to see what it looks like in just. So here's what it looks like. Wait for it. There it is. So it's one of those that has branches. It has asymptotes, and then it's got these branches. So I was just writing it that way to see it's a reciprocal. All right. How about it? Any questions? No. So that's a quick, I guess it's not quick, but it's a way of testing your equation to see if it has symmetry at all. All right. If there are no questions there, then let us boogie. Whoa, hey, wait. I'm out. Single file, lady in the lead. Do-si-do.
what was that? You didn't do anything.
I didn't do anything. Everyone started to react. Got the hand.
I was the only one that reacted.
Got people saying that these things are cute. We got all kinds of weird, bizarre things going on in here today. Weird and bizarre. Bizarre weird. Got a guy talking about growing a mullet. Jeez, you're a soccer player, aren't you?
I am a soccer.
See, I was a soccer player too, and when I was in high school, we had mullets. It was like the thing to have.
You don't talk to each other. Wow, thanks.
She thinks she is.
That's what I say every day.
Anyway, here we go.
Really right.
I'd like you guys to try. I'd like you guys to try A, B, and C. Oh, if you want to be adventurous and try D and E, but at least give me A, B, and C. Partner up with somebody. See if we can get the graphs for these things. The equations you see on the right, those are just for me that I can use my quick little graphic feature. So there's the original, y equals 2x minus 3, and then here's what I'm doing to them. Negative of the function, negative inside the function, absolute value of the function. Let's see what we get. So here's our equation for y equal, there's the graph for y equal 2x minus 3. Just a linear function. And now we're going to base all of these changes off of that. So our first change for A, notice it says the opposite of the function, or a negative on the outside means we're going to reflect everything vertically. So over to the right is just that same equation with that change. So it looks like y equal negative quantity 2x minus 3. If we put the negative on on the inside of the function. Then we would get negative 2x minus 3, which is where that one is coming from. But let's first of all, before we go any further, let's see what we would get with this first equation. What would the graph look like? This is now reflecting over the reflecting over the x-axis. So you should have had something that looks like that. Purple line there. All we're doing, we take our original x values, our y values, excuse me, and we're flipping them over. So, for example, if I'm looking at that coordinate, which is 3, 3, I would be at 3, negative. You guys have that one? We good on that one? All right, this next one. So let's get rid of that guy. Hey now. Didn't I just get rid of you? There we go. Here's the next one. This is now reflecting over the y-axis. How about it? Does yours look something like that? Yes? Go away. Go away. Leave me. What the heck? All right. Next one. I can't do that one. We're going to do this one by hand. So absolute value. What is the absolute value going to do to this graph? So the question was, why did I choose to rewrite it like that? Does anyone know, perhaps, why I did that? What's up there, Steve? Huh? Okay, something about it, you're okay. Kind of. What were you going to say, Cameron?
Oh, the HBK.
Yes, there you go. So every function, I can think about h's and k's, which are left and right translations, right? In this case, what we do, if I want to think about an h, I want to see a coefficient of 1 in front of my x. So by factoring out that 2, the way I've done it here, that 2 is now a horizontal shrink of 1/2. And now I have x minus 1, or 1.5, or x minus 3 halves, which means I move my graph to the right 1.5, and then that's where my starting point would be for this thing. So that is what I'm doing when I've got a coefficient in front of my x and an absolute value function, or in any function, actually, I can do this. Factor that leading coefficient out, and then you'll be left with a stretch factor horizontally, a stretch or a shrink factor horizontally, and you'll be left with what my right and left translation is supposed to be. Yes?
Do you have to do that way?
The other way you can graph this is just put a table together. Yeah, you just put a table together. All right, so what would this look like then? Here, I'm going to show you related to critical movements for absolute value graph. So our absolute value critical movements, if I did a negative 2, it would be a 2, negative 1, 1, a 1, 1, and a 2, 2. This 2 out here makes all of these x values multiply by a half. They become half this big. So if I'm going to graph this thing, I've got that telling me that I have a horizontal translation, which is a movement of 3 halves to the right. And that's where I would begin this V. Is I kick it over to 3 halves, start my V right there, and then now I apply all of these movements from that point. Again, this is one of the ways you can do it, using parent functions. The other one is to do, just plug in t-table values and do it as same thing. So 1.5, there I am. And if I am following my table, negative 2, 2 actually becomes negative 1, 2. So left 1, up 2. Right 1, up 2. And I would get a graph looking like this. We have haven't spent a whole lot of time talking about this notation, so let me just introduce something to you here. A, B, X plus or minus C plus or minus D. This is our generic transformation equation. And what do the pieces mean? This is a vertical stretch or shrink. So it's vertical stretch or shrink is what the A does. The B is a horizontal stretch or shrink. And it actually affects your X and Y movements by 1 over B, whatever that is. Whereas this gets affected by, your vertical movements gets affected by A. Multiply everything by whatever A is. It's a fraction, you multiply by a fraction. Then you have C, which is a horizontal translation. So we're thinking right or left. And then D is a vertical translation. And we've seen all of these actually, with the exception of B. So up or down. Yeah, we've seen all that stuff before with the exception of the B. So if I were to take that equation and apply it to something we've done before, here's one. We know this. 3 times quantity x plus 4 squared minus 2. We know that that's a parabola that went left 4, down 2, and then it's stretched by 3 vertically. So we've actually played with all this with the exception of this. All right. So that's called our transformation equation. It's generic to any function that we have that we're working with. Cubics, roots, whatever. We can apply it to anything. Okay, so did anyone happen to try D or E? Crafting wise? No? So those are going to have to think about with a table, because I don't have a parent function that is related to absolute values of a binomial before. We haven't done that for 2 variables. And then we haven't really talked about absolute value y, we always done absolute values of x's. So here we're just going to create some tables to see what we get. Should we do it together? You guys want to try it on your own? Together. All right, we're going to go together. Do I have enough room here? Maybe. Maybe not. Move this over. Maybe we have room. Okay, let's put our table together for D. All right, let's try it for D. I put a generic table. Let's just pick some points. Let's put a -2 in there, a -1 in there, a 0 in there, a 1 in there, and a 2 in there, and see what we get for y. I put a -2 in there. What does y have to be? 0 or a 4. 0 or a 4. I want to create inside of this absolute value, I want to create a 2 or a -2. I can create a -2 by y being equal to 0. I can create a +2 by y equal to 4. So I'm going to get 2 answers there. -1, what am I going to have y be? -1 or 3. 0 for an x, 2 or a -2. 1 for an x, 1 or a -2. negative 3, right? And then 2 for an x, 0 or a negative 4. So here I'm getting some weird thing going on. I got 2 y's for every x. So let's see what this thing looks like. So negative 2, 0, and 4. Negative 2, 0. Let's get rid of this other graph. It's kind of in our way here. Don't need to anymore. All right. Negative 2, 0, and then 4. Negative 1, negative 1, 3. Negative 1. Oh, that's positive. Negative 1. So there's 3, and there's negative 1. And then 0, 2, negative 2. So negative 2 and positive 2. And then 1 and 1 and 1 and negative 3.
Parallel lines.
Look at that. 2 parallel lines. Well, that's kind of strange. Yeah. We have 2 parallel lines there. The other way you can think about this problem, since it's absolute value, you can think about positive guts and negative guts. And then you can just graph them as 2 lines. Same thing. Get the same. You don't have to use the table if you do it that way. All right, what about E? What are we going to do there? Let's check out E's table. Running out of room here. Should we move some stuff? Can I move all of this?
I'm sure you could.
Well, I'm going to. I'm going to move it. Come on. Move. There we go. Move 2. Uh-oh.
Here's where we're in the problems.
There we go. All right. So let's check our table here for E. Putting in x's, y. Okay, what if I put a negative 2 in? What does y have to be? If it's positive 2, I'd have negative 4. So is it possible? Nope. But any negative that I use, no solution. What about I use the 0?
No solution.
Yeah, once again, no solution. All right, so it looks like we're going to be testing some positives then here. So if I put a 1 in there for x, y can either be a 4 or a negative 4. If I put a 2 for x, I can be 2 or a negative 2. If I put a 3 for x, no, we don't want to do a 3 because I don't want to deal with fractions. Let's do a 4. If I put a 4 for x, I would be a 1 or a negative 1. Well, once again, I got these weird things going on. 1, 4, and negative 4. And then 2, 2, and negative 2. And then 4, 1, and negative 1. So what this is it looks like I've got some branches. Some asymptotes. All right, so again, those aren't parents. I just gotta have to put a t-table together for those. All right, what do you think? Any questions here? Not that bad, is it? Yes,
For C, you had a B. I remember. How did you get that B?
how did I get this 2 that's hanging out here? This guy right here. I factored a 2 from the top. So from this equation here, I pull out a 2, and I'm left with an x minus a 3 halves.
Yeah, right there.
Does that make sense?
But like, how did you get the B shape that?
Oh, how do I get the B shape? Every absolute value, y equal absolute value of an x thing is going to be a B shape. So if I were to just plug in some x's in here, I'm going to find out that I have a B shape.
That's just beautiful.
All right. There are no further questions.